So next, we're going to have Ziyan from RISE talk about using visual feature space as a pivot across languages.
Hi everyone, today I'm going to talk about using visual feature space as a pivot across languages. I am Ziyan from Rice University. I'm a PhD student. There are various languages across the whole world, but essentially all these languages are used to describe the same visual space. As we can see in this example, for the same image, there are hundreds of languages can be used to describe the content in it. We are interested in the topic that if we can use the shared visual space to transfer information between languages. First, I want to introduce how to map image to text. Image captioning task is the model is supposed to learning the mapping between image and text descriptions. Most research about this topic focus on generating captions, like English captions for images. If we expand the task to multilingual background, it's more challenging since different languages will have different description styles. In the shown example, we can easily map the keywords in generated captions back into the image. Even though English and Japanese are very different languages, they are still sharing the same visual space. However, image captioning models are not perfect. The image confuses the model. Here in this example, the generated sentence actually mistakenly describes the person in the image as a woman, even though the human can recognize correctly that this person is a man. Without additional information, it's hard for the model to improve its generated captions quality. Therefore, we would like to use another language as additional information to help the caption generation for one language. Next, let me introduce the overview of our method. Here is a multilingual image captioning task for 3 languages, English, German, and Japanese. And each language will have one separate text decoder. During the training time, the CNN image encoder takes image as inputs and generates image features. Then the image features are fed into different text decoders to generate captions for different languages. During the inference time, we are interested in transferring information from one language to another. We choose a source language and a target language. We want to combine source language's caption information and image information together to generate the captions for target language. We can do it for any pair of languages. Here, English is a source language and German is a target language. We can also use English to help Japanese, using German to help English, German to help Japanese, and Japanese to help English, Japanese to help German. Furthermore, to purely test the information transferring between language pairs, we can even get rid of images. Therefore, we only use captions. This looks more like machine translation, but the information is not transferred between languages directly. Instead, it will go through a shared CNN space. We can choose English and German also here as source and target. Also from English to Japanese, German to English, German to Japanese, Japanese to English, and Japanese to German. We will have 6 possible language pairs if the decoder number is 3. Here I will introduce some more detailed structure of the model we are chosen. We choose to use transformer. Originally, transformer is designed to do machine translation. It consists of self-attention and cross-modal attention mechanisms to generate mapping between source and target languages. However, in our case, we hope the transformer to learn the mapping between image and text instead of text and text. Our transformer encoder will take image features as a sequence of features, just like a long sentence text feature. Then we use transformer model for multilingual image captioning. The transformer encoder will be shared by all the transformer decoders, and different transformer decoders will generate captions for different languages. During inference time, in the first case, we have both image information and text information from source language, and we want to generate captions for target language. The input image will go through, say, an encoder and generate captions for two languages. Here we have English and Japanese. Then we will assume we have the ground truth caption for the source language, which is Japanese here. Next, we will calculate a partial loss between predicted Japanese caption and the ground truth Japanese caption, and do backpropagation till the intermediate image feature in, say, an encoder. We predicted Japanese captions, calculated loss, and updated intermediate image features iteratively. After several iterations, we can get updated intermediate image features. Using this updated intermediate image feature, we will have generated an updated feature map and go through the decoder for the target language to get an updated English caption. We compare the provided true Japanese caption and the new generated English caption, and you can see there exists information that cannot be obtained by using image as input only. The English force green water is definitely coming from the Japanese word Midori no Nomitsu. Let me define the process more formally. The image input is I, and the intermediate image feature in the first step that generates predicted English and Japanese caption is noted as Z equal to GI. G is the layers that generate the intermediate image feature. Y source and Y target are predicted English and Japanese captions from Z. T source is the ground truth Japanese caption. Then the updated intermediate image feature Z hat is calculated by minimizing the energy function that measures the compatibility between Y source and Y target. We use cross entropy loss here, actually. After obtaining the updated Z hat feature, we can get an updated caption for the target language as Y hat. In the second setting, we get rid of image information during inference time and only feedback source language caption to generate target language caption. We input a noise image to, say, an encoder and generate in the first round meaningless sentences for English and Japanese. Then similarly, we assume we know the ground truth Japanese caption and do backpropagation, calculate the loss, and get an updated intermediate image feature. Then we use the updated intermediate image feature to get an updated English sentence. By comparing the generated English caption and the provided true Japanese caption, we can get some mappings. For example, two birds actually come from the Japanese word toriga ni biki. To define more formally, the noise image epsilon is sampled from a uniform distribution between 0 and 1. Then the intermediate image feature Z is obtained by epsilon. Similarly, Y target and Y source are predicted English and Japanese captions. T source is the ground truth Japanese caption. Z hat will be updated, actually only use T source. And finally, Y hat for target language will be generated. To evaluate our method, we conduct experiments on two datasets. Both of them have images and multilingual captions. We use three widely used metrics to evaluate the performance of our method. In the first two rows, we show the baseline generated caption obtained only from images. Next two rows show the generated target captions from image and the source language. Finally, last two rows show that without a useful image, how information can be transferred between languages. As we can see, with the help from English, we can get better captions for German. Similarly, German can help English. English helps Japanese. Japanese help English. German helps Japanese. And finally, Japanese help German. The improvement in caption generation is consistent through all the cases. For only transferring information between languages, we can also get some reasonable results as shown here. Next, I will go through several qualitative examples. If the input image is shown here, like this, the generated Japanese caption will be a bicycle is parked in front of the shop. It's not accurate enough, so with the help of English caption, the Japanese caption will be improved as a person riding a bicycle is running on the road. As we can see, more details will be provided with the help of the ground truth English caption. Here are more examples that we use German to help English caption generation. Words and also use English to help Japanese caption generation. Words in the same colors have similar meanings. Here is Japanese help German and German helps Japanese. So if we only use one language caption to help the generation for another language, here are some examples. Here is we use German caption to generate Japanese sentences, or use Japanese caption to generate English sentences. As we can see, several important contents can be mapped back to the provided caption. Here are more examples about it. So also German to English, Japanese to English, German to Japanese, and Japanese to German. In conclusion, our method demonstrates we could improve image captioning quality during inference time for all language pairs. Our method shows visual space could transfer information between language pairs, and the image captioning model can learn mappings across languages similar to machine translation. We could use a single model to transfer information between several different language pairs. And thanks to my collaborators, my advisor Vicente, and my collaborators Leticia and Frank. Thank you for listening. And if you have any questions.
All right, thank you, Ziyan. So, quick question: you plan to expand this work to more languages?
Yes, it's still in process, but actually it's a little difficult to get the in image captioning data for multilingual classes. So I think if we can get a model with, if we can get a data set with more than 3 languages, for example, if we can get the image captioning model for also Korean or French, then it's possible that we will expand this work to more languages.
We got one more question. Could your approach be useful for deciding which type of data, language, or images should be collected, likely with different costs, for improving the accuracy of predictions?
I'm not sure what does it mean by proving the accuracy of predictions here.
So what is more important here, language or
I think to get a better result, for example, for the sentence generation for another language, it's better that you can combine both language and image, right?
Okay. So it's value label pairs. Okay. Well, thank you so much. All right.